Alright, and if my voice starts dropping off, just let me know, alright, and I'll repeat it. Is it okay? Just take it off? Okay. Okay, I will take it off. Okay, so we were talking about muscle fatigue, right? And my throat muscles are probably going to get fatigued at the end of this lecture because we have no microphone. Feel free to come and sit forward. We have a lot of open seats here. So if you can't hear me, can you guys in the front hear me pretty good? Okay, great. So you have that option as well. So we'll see that muscle fatigue is going to be linked pretty closely to substrate depletion. All right? And we talked about three kinds of substrates. We talked about carbohydrates, proteins, and fats. And proteins are going to be mainly used when a person is in starvation. So we only consider the role of fats and carbohydrates in the synthesis of ATP. So we'll see what happens during muscle fatigue, and then we're going to move on to talk about types of muscle contraction. So when you talk about types of muscle contraction, we're going to divide it based on two things. The first one is based on the load carried by the muscle, and secondly, it's going to be based on the length of the muscle as well. All right. So as the muscle length changes, if it's going to increase, decrease, or remain the same, there can be different types of contraction. And then finally, we'll talk about fine-tuning of the force response. And you can see that there's a picture of a regulator here. And what we mean by fine-tuning is that the amount of force which is produced by a muscle can be regulated depending on the load which is carried. So this can happen in several ways. I'm going to just mention three ways. It can happen through motor unit recruitment, secondly through twitch summation, and thirdly it can happen by the force length relationship. So among these three things what I've mentioned here, the first two, they are unique to skeletal muscles, whereas the third one, the force length relationship, it's common to both skeletal and cardiac muscles as well, the force length relationship. So with that overview, let's start with what do we mean by muscle fatigue. So a muscle is said to be fatigued when it can no longer perform at a required level of activity. All right, a muscle is said to be fatigued when it can no longer function at a required level of activity. And what we mean by a required level of activity could be that a certain load can no longer be borne by the muscle, or maybe an activity for a certain duration of time cannot be performed. So it could be in terms of what is the load carried by the muscle, that's going to decrease, and also the activity cannot be carried out for a certain duration. So we see that fatigue is mainly correlated with the depletion of metabolic reserves. Right? It's going to be mainly associated with the depletion of metabolic reserves. Now we need to see that there are two ways in which these reserves can be depleted. They can be depleted by aerobic metabolism or by anaerobic metabolism. So there are two ways in which these reserves can be depleted. As far as the aerobic metabolism, which will lead to the depletion of these resources, is experienced by a person who is engaging in an endurance activity. For example, it could be running a marathon, maybe if you're not as capable, maybe running a half marathon, or maybe even 5 or 6 miles, right? And when you're engaging in an aerobic activity, it's not going to happen at a very high intensity, and so fatigue will eventually set in when the reserves are all depleted, especially the carbohydrates and the fats. So when that's depleted, that's when fatigue sets in. But when you're thinking about anaerobic metabolism, right, which is happening when you're working out at a very high intensity, maybe sprinting or maybe doing push-ups, in such cases we see that it is the anaerobic metabolism which is happening, and along with that, along with the depletion of the substrates, there are also other things happening as well, and that's what I want to highlight here. So we see that when you have glucose being converted into pyruvate through glycolysis, and there is a lack of oxygen because the intensity of the activity is very high, you want the ATP to be generated quite quickly, pyruvate is going to be converted into lactate, and lactate can in turn be converted into lactic acid. The difference between lactic acid and lactate is just the presence or the absence of a hydrogen ion. And lactate, it's going to be sent to the liver where it can be converted back into glucose, and this I mentioned is the Cori cycle. It takes place very quickly so that ATP can be generated quickly, but then it is not very efficient. Now, not all of this lactate is going to be converted into glucose, and so there will be the buildup of lactic acid in the muscles, which will cause a decrease in the pH. And as the pH is decreasing, it can have other effects as well. For example, it's going to cause a reduction in the enzyme activity. I want to make you remember what we discussed, I believe, in the very first week of classes. I told you how enzymes are proteins, and if you change the environment of a protein, the structure is going to be affected, and as a result, the functioning of that enzyme is going to be affected as well. And last week we talked about several reactions which take place in the aerobic and in the anaerobic pathway, and all of those reactions require enzymes, and if the activity or the structure of those enzymes is affected, it will in turn have an impact on muscle performance. Does that make sense? How changing the environment of those proteins can affect their function. Next, we find that an acidic environment is also going to have an impact on how effectively calcium can bind to troponin C subunit. I told you that calcium binding to troponin C is essential for the thin filament to transition from the blocked state to the closed state, and that is the very first step for force generation. And if calcium cannot bind effectively to troponin C, the amount of force generated is going to decrease as well. This is the second thing which happens as a result of increased acidity. Thirdly, the lactic acid can also start activating the pain receptors which are in the muscles. So these are free nerve endings which can be activated by lactic acid, and when you're in pain, your motivation is going to start dropping down, right? You don't feel motivated to continue doing whatever is causing that pain. So it's not only physiological reasons which can lead to fatigue, but also psychological reasons can also influence fatigue as well. And that's why it's not uncommon to notice that folks who are engaging in very high intensity activities, they may listen to very upbeat music, all right? And I like to jog, not run, and I save for the last mile or so I might listen to upbeat music, but otherwise it'll be some story or a sermon, right? But the last mile I need something to get me past the hurdle, so I would listen to upbeat music. Right, so this is what is happening during muscle fatigue, especially during anaerobic metabolism. Are there any questions before we proceed? Okay, so fatigue is what is experienced while you're exercising a given muscle. But we see that several hours after an activity, it can lead to what is known as DOMS, or delayed onset muscle soreness. So DOMS is going to usually begin several hours after a physical activity, and it's going to last for a few days, maybe 2 or 3 days. Is anybody in this room currently experiencing DOMS? Okay, great. Yeah, from what I worked out last week, I am in that same group as well. So the question is, what is causing DOMS, right? And there's some controversy over this, but there are 3 proposed mechanisms for why we feel pain several hours after a specific exercise. Firstly, we see that the muscle fibers or the muscle cells can be damaged during an exercise, and when these cells are damaged, the intracellular content will be released. And examples of this intracellular content may be enzymes which are inside the cell, the loss of myoglobin. Myoglobin is what binds oxygen. So the release of these intracellular components can activate the pain receptors, and that can lead to the soreness which is experienced. Secondly, there can also be muscle spasms, and muscle spasm is just the involuntary contraction of muscles, and this could be caused by a number of reasons, like dehydration or maybe just overexertion. Like if you've not done an activity for a long time, such as say shoveling the snow, and then after you shovel snow for the first snowfall, you might feel increased soreness, right, because of increased exertion. Thirdly, the connective tissue, which is linking the muscles to the bones, or even the connective tissue surrounding the muscles, can also be affected. There could be micro tears, and that can also activate the pain receptors as well. And we find that one way in which this delayed onset muscle syndrome can be reduced is by engaging in stretching, right? But there is some limited evidence on this, so see if it works out for you or not. All right. So with that, are there any questions or comments on DOMS or muscle fatigue? The main difference is one is happening during the activity and the other one happens several hours after the activity. Okay, now let's move on to talk about the effects of aging on the muscular system. So we see that all of the effects which we are going to talk about as far as aging is concerned is linked to one aspect, and that is the decrease in protein synthesis, right? So if you think about the decrease in protein synthesis, all of these characteristics which I mentioned next will make sense. So as we age, the muscle fibers are going to decrease in their diameter, and this is because of reduced protein synthesis. And also the elasticity in these muscle fibers will decrease. I told you that elastic properties is due to a protein known as elastin. So if you have overall decrease in protein synthesis, the elasticity is also going to decrease. And consequently, the ability to recover after muscular injuries is also going to reduce as well. So you cannot bounce back as quickly after a very intense workout. And so overall the tolerance for exercise decreases as well. And so as we get older, it is more important to engage in regular exercise, and it's not as important to engaging in very demanding exercises, because that could be counterproductive, especially if your body does not have a high enough ability to regenerate the damaged tissue. Okay? Any questions at all on aging and exercise? Okay. So now we're going to talk about various types of muscle contraction, and I told you that we can consider the types of muscle contraction based on two things. One is the type of load carried on it, and the second is the muscle length as well. So the first one is isotonic contraction, and what we mean by isotonic contraction is that the load carried by the muscle is not going to change. All right, so if this bottle weighs like half a pound, it's weighing half a pound no matter what, right? So that is when I'm carrying a weight where the load doesn't change, that's an example of isotonic contraction. The next one is isometric contraction, where the length of the muscle does not change, right? And I'll give you examples of these types of contraction. So under the context of isotonic contraction, we see that the muscle length can either shorten or increase. Okay, so notice here that here is a picture showing you isotonic concentric contraction, where the muscle length is going to shorten. And in order for the muscle length to shorten, the force generated by the muscle has to be greater than the load which it is bearing. I'll repeat, in order for the muscle to shorten, the force generated by the muscle must be greater than the load it is carrying. And so they're given some numbers here. Notice this weight is 2 kilograms, and the muscle is able to shorten because it's generating more force than the load which is being which it is carrying. Now on the other hand, let's say the amount of force generated by a muscle is less than the load, as shown in the second example. You have eccentric contraction, where the muscle is lengthening even though it is trying to contract. And so they've shown here that the weight is 6 kilograms and the force generated by the muscle is less than the load it is carrying. And here you see that isometric contraction is where there is no change in the muscle length, because the force generated by the muscle is equal to the load it is bearing, right? That's why the muscle length doesn't change at all. And so these three types of contraction may seem very abstract, but let me give you a real life analogy. All right, how many of you have done a bicep curl at least once in your life? Okay, great, everybody, right? So we find that when you flex the arm and you raise up the weight towards you, you're causing the biceps to contract. And the reason the bicep is able to contract is because the force generated by the bicep is greater than the weight which is being carried. And so you have concentric contraction going on when you're flexing the bicep. And as you hold the weight in place, at that point you're having isometric contraction because the length of the muscle is no longer changing. And then as you lower the weight, you are engaging in eccentric contraction because the muscle is lengthening as the weight is being carried down. Now it can be a bit counterintuitive. How can the muscle lengthen while it is contracting? Because you know that in order for contraction to take place, you have the sliding of the thin filament over the thick filament. So it may seem a bit counterintuitive, but think about this. If there was no contraction happening, the weight would just drop down, right? But the fact that you're able to lower it in a controlled manner means that there is eccentric contraction taking place. Is this clear, or is there any clarification needed? I actually already wrote the questions for the exam in the muscular system. So guess what? There's a question on this. Anyone needs clarification? Okay. One last point I want to mention before we proceed is that the speed of the shortening is going to be proportional to the load. It's going to be inversely proportional to the load. So if you're carrying a very light load, then you can contract the muscles very quickly. The muscle can shorten at a very fast rate, but as the load gets heavier, it's going to contract at a very slow rate and shortens at a slow rate. Think about this. You take a 5-pound dumbbell and you try to curl it, you will curl it pretty quickly, right? The muscle shortens pretty quickly. But then if you move to a 50-pound dumbbell, I don't think I can do this anymore, but then you try to curl your biceps, it's going to happen very slowly because the greater the weight, the slower the rate of shortening. Does that make sense? Okay. Since none of you have questions, as usual, I have a question for you. Alright, so isotonic eccentric contraction occurs when you blank. Raise a dumbbell by flexing the arm, lower a dumbbell by extending the arm, hold a dumbbell in place. None of the above. I don't know. Okay, we have lots of responses.
I guess makes sense.
Alright folks, let's bring it back together. Alexander, do you have anyone in your group who wants to share? Anybody? Yes?
The eccentric contraction is going to happen when you lower the dumbbell by extending the arm because you're lengthening the muscle and you're getting like a deep stretch.
Yes, so the answer B is the right option. So eccentric contraction happens when you lower the dumbbell by extending the arm because the muscle is lengthening. Okay, does that make sense, folks? Yes? Alright. So now we'll talk about how the force generated by skeletal muscles can be fine-tuned. So if you notice these three pictures here, you see there's this guy trying to push an empty cart, no effort required. Thanks, Addy. And then once this cart is filled with a lot of things, you see that a lot more effort is required to push that cart, right? And so we see that the amount of force generated by the muscle is going to change according to the need. So there are three ways in which this can happen. The first one is the recruitment of motor units. Secondly, you have twitch summation, and thirdly, you have the force length relationship. All right, so we're going to talk about each of these types of ways in which the force generated can be controlled. So when you think about the recruitment of motor units, the question is, what is a motor unit? So a motor unit is referring to a single motor neuron and all the muscle fibers it is going to innervate. I'll repeat. A motor unit is referring to a single motor neuron and all the muscle fibers it's going to innervate. So then the next question is, what is a motor neuron? I hope you all were paying attention in the nervous system. Motor neuron is what is going to carry signals from the central nervous system to various target organs like muscles, right? And these motor neurons will carry signals to the muscles. And so we see that there can be small motor units and large motor units. Small motor units, they will innervate fewer muscle fibers, whereas a larger motor unit will innervate more muscle fibers. So how will this motor unit be activated? We see that it's all going to happen at the neuromuscular junction, and this is a figure we talked about previously. In the neuromuscular junction, you have this presynaptic terminal where there are a lot of vesicles filled with acetylcholine, and moment the signal is received from the central nervous system to this efferent motor neuron, it will release acetylcholine, which will bind to ligand-gated receptors. Specifically, it binds to ligand-gated sodium channels. And so as sodium starts entering into the cell, we see that the threshold is going to be reached in the muscle. And once that threshold is reached, it causes the opening of sodium channels, voltage-gated sodium channels, which cause a rapid depolarization. And then once the membrane potential is around 30 millivolts, the sodium channels close, potassium channels open, and that is the rapid repolarization, right? And so this action potential will travel down the T tubules in the sarcolemma, and that will lead to the muscle contraction, right? So this is something we talked about in the excitation contraction coupling, and I just want to repeat it in the context of the motor unit recruitment. So we find that organs in the body where you have these small motor units would be like the eye muscles, where you have very fine movement and also quick movement, whereas in the larger muscles like the legs, you have very large motor units. So you would have maybe a dozen fibers in the motor unit in the eyes, whereas the motor units in your thigh muscles maybe have thousands of muscle fibers which are being made to contract. So we find that the increment in force for a smaller motor unit recruitment, it will be a lot smaller, whereas when larger motor units are being recruited, the amount of force generated will be significantly greater. The incremental steps will be much larger, right? And as the weight is greater, the brain will send signals to recruit more motor units. If the weight is lighter, then you will have fewer motor units being recruited. Is that making sense? Yes? Okay, so this is the first way in which the force generated by the skeletal muscles can be regulated. Now the second one is known as twitch summation. And so to talk about twitch summation, I want to point out that there are two graphs here, right? In both these graphs, the one on the top panel and the one on the lower panel, both have time on the x-axis. Okay, on the x-axis, both have time. On the lower panel, we find that on the y-axis you have the membrane potential shown, and on the above panel you see the corresponding force response in response to a action potential. So in the lower panel you have the membrane potential, and we'll see the corresponding force response to that action potential. So we see that when there is an action potential, in the skeletal muscle cell will be around 1 to 2 milliseconds. And in correspondence to that, you have a twitch where you have an increase in the force generated by the muscle, and then there is a decrease in the force generated as well. Now the question is why? Why is there this twitch response? Why is there this initial increase in force, and then why is the decrease in force? Now the increase in force is because the action potential which travels down the T tubule causes calcium to be released from the sarcoplasmic reticulum, leading to actin-myosin interaction, and that's why you have this force being generated. And then the next question is, why is this force decreasing back to normal levels? The answer is calcium is being moved back into the sarcoplasmic reticulum, and that's why you don't have any more actin-myosin interaction, and so this force decreases again. Does it make sense? Yes? Where you have this twitch response? Okay. Now we find that when two action potentials come in rapid succession, we see that there is this concept known as twitch summation, where the amount of force generated is going to be much greater. Right? And the question is why? So we see that in response to the first action potential, a certain amount of force is generated because some calcium has been released from the sarcoplasmic reticulum, and there is actin-myosin interaction. And before that calcium can be taken back into the sarcoplasmic reticulum, we find that there is another action potential which causes more calcium to be released, and since there is more calcium available, the amount of force generated will be greater, right? And that's why this is called as a twitch summation. And because eventually all the calcium will be taken back into the sarcoplasmic reticulum, notice that the force decreases back to the pre-excitation level. Does it make sense? Yes? Okay, but when you have action potentials in rapid succession, we see that the amount of force generated will gradually increase and reach a maximum level known as tetanic contraction, because the maximum number of cross bridges which are available have been recruited, and that's why you have this steady state of maximal force being generated. Does that make sense? Yes? Okay, now here's a question for all of you. Can we have summation of action potentials in the cardiac muscle? We see this in the skeletal muscle. Can we have it in the cardiac muscle also? It's okay. Few people say yes, a lot of people say no. One person says I don't know. Okay. Alright, let's explain why that's the case. Alright, so the answer is actually no. Right? And the reason why it is no is because the shape of the action potential in the skeletal muscle cell is very different than the action potential seen in the cardiac myocyte. Alright, the shape of the action potential is very different, and let me tell you what's the difference. So we see that here is a graph showing you membrane potential on the y-axis and time on the x-axis, and there is a stimulus which causes the opening of voltage gated sodium channels. Exactly what is the stimulus, we'll talk about it when we discuss the cardiovascular system. But the stimulus causes the opening of the voltage gated sodium channels, and so there is this rapid influx of sodium into the cell, and then at plus 30 millivolts you see that the sodium channels will close and the potassium channels open, and you would expect to see a rapid repolarization as potassium ions leave the cell. But instead, as potassium is leaving the cell, calcium starts coming into the cell, and so we see that this plateau phase will result. So the efflux of potassium ions is balanced by a influx of calcium, right? And that's why there is this plateau phase which will result in. Now keep in mind that the amount of calcium which comes into the cardiac myocyte isn't as much, but the incoming calcium will in turn interact with the ryanodine receptors in the sarcoplasmic reticulum, and that leads to this calcium induced calcium release, and so even inside from the sarcoplasmic reticulum calcium is going to be released. So the amount of calcium in the cardiac myocyte increases, and that's why you have this plateau phase. This type of calcium-induced calcium release is unique to the cardiac muscle. It doesn't happen in the skeletal muscle. So eventually we find that the calcium channels will close, and so potassium ions can leave, and so you have the rapid repolarization. So the key difference between the cardiac and the skeletal muscle action potential is this huge refractory period, and during this refractory period the cardiac muscle cannot be re-stimulated again to contract, unlike what we saw in the skeletal muscles. So the answer to the previous question was no, we cannot have a summation of the action potentials in the cardiac muscle. So here's a picture where we are comparing the action potential and the corresponding force response in the skeletal muscle shown in the above panel and in the cardiac muscle in the lower panel. So in both of these figures, time is shown on the x-axis, and on the left hand side y-axis you see the membrane potential shown in green, and on the right hand side you see the corresponding force response. So in the skeletal muscle the action potential is only 1 to 2 milliseconds, and so whereas the force response is going to be around 100 milliseconds. So it's possible to have multiple action potentials before this single force response ends. Whereas in the cardiac muscle you notice that this force response shown here in purple is going to last almost as long as the action potential itself. I'll repeat, in the cardiac muscle this force response is going to last almost as long as the action potential which triggers it. And this is extremely important because we find that if there is this refractory period here for a long time, then the cardiac muscle has got sufficient time to relax, and the relaxation of the cardiac muscle is important so that it can fill with blood for the subsequent beat. If you have tectonic contraction, the cardiac muscle, it's not going to relax. As a result, it won't fill with blood, and so the amount of oxygenated blood sent to the rest of the body will be severely impaired. Does it make sense? Why this is important? Okay, so we're done with twitch summation. That's the second way in which force generated in the skeletal muscle is regulated. And the final thing is the force length relationship. So in this figure here you notice force generated is shown on the y-axis, and the muscle length or the sarcomere length is shown in the x-axis. So sarcomeres are the basic structural and functional unit, and we see that as you change the sarcomere length, the amount of force generated can change as well. So initially there is an ascending limb from point A to point B, where if you increase it from say 1.2 micrometers to around, let's say, 1.7 micrometers, there is this dramatic increase in force generated. And then if you go from, let's say, 1.75 to around 2.4, we see there is still an increase in force, but then it's not going to be as dramatic, and eventually there is this plateau region. However, if you start stretching the sarcomere beyond, let's say, 3 micrometers, we see that the force starts decreasing. So we notice that there is this ascending limb, plateau region, and then a descending limb as far as the force length relationship is concerned. Now the question is, why is this the case, right? And we see that the force generated at any given sarcomere length is going to be proportional to the number of actin-myosin interactions. So if you have more actin-myosin interactions, you'll have more force generated. Less actin-myosin interactions, less force generated. Okay, and we see that what this length of the sarcomere does is it's going to influence the total amount of overlap between the thick and thin filaments. So if you have optimal overlap with the thick and thin filaments, there will be more actin-myosin interaction, leading to more force generation. So if you look at this panel on the right hand side, it is showing in A you see that there is this single thick filament, and on either side you have thin filaments, and at a very short sarcomere length you have overlap between these thin filaments, and so you don't have as much interaction between actin and myosin, right? And then if you come down to B, there's a slight increase in the sarcomere length, so there's a little more interaction between actin and myosin. In picture C and D, you have maximal interaction of actin and myosin because it's at an optimal length. Now, stretching the muscle beyond this, it's going to decrease the amount of actin-myosin interaction, and that's why you see a decrease in the amount of force, and that's why there is this descending limb being represented. Is there any questions? Does anyone need clarification on why you have the ascending limb, why you have the plateau region, and then why there is this descending limb in the force-length relationship? Yes?
Does the optimal or the sarcomere length that produces the most force, does that occur for every sarcomere at the same?
Yeah. So it would be occurring at multiple sarcomeres.
Is it like typically around joint angles of 90 degrees?
At what? Say it's typically at what?
Around joint angles of 90 degrees.
I'll explain the difference between skeletal and cardiac muscle in a second. That it'll make sense the moment I tell you the next point. Any other questions on? Yes.
So would this just apply to isotonic contractions, or is this somehow applied to isometric contractions? Just keeping it there.
It will apply to both. So when you have isotonic contraction, it's going to change with time, right? But I think to answer both your questions, you need to realize that physiologically the skeletal muscles will function at this plateau region, whereas cardiac muscles, they're going to function in this ascending limb. So one of the reasons why skeletal muscles are functioning in this plateau region is because they are going to be connected to the bones, and so they are already in the plateau region and they will generate the maximal amount of force, whereas in the cardiac muscle it's not connected to anything, and so it will function in this ascending limb. Okay, so we see that the way the cardiac and skeletal muscles respond to changes in force is quite dramatic. So here is a picture showing you the normalized force shown in the y-axis, and the reason we need to compare normalized force is the skeletal muscles will produce more force than the cardiac muscle. You can't bench press using the cardiac muscle, but skeletal muscles can carry a lot more load, right? So we need to see the comparison in the normalized forces on the y-axis, and on the x-axis you have the sarcomere length shown, and this pink region is showing you the physiological range where the cardiac and the skeletal muscles are functioning. So if you have a 10% increase in the physiological range of the cardiac muscle, the amount of force increased is around 50%, whereas in the skeletal muscle, for a similar increase in muscle length, you only have a 15% increase in force, because the skeletal muscle is in the plateau region, whereas the cardiac muscle is in the ascending limb. And so this steeper force length relationship in the cardiac muscle is going to allow it to adjust the force generated based on how much blood is filling the ventricles. So this is known as the Frank-Starling law, where the cardiac muscle will produce as much force as dictated by the end diastolic volume. So this is kind of like a rubber band. The more you stretch it, the more force it produces. The less you stretch it, the less force it produces. But we know it's not functioning like a rubber band. It's because of the force length relationship and the cardiac muscle functioning in the ascending limb. Yes?
So the skeletal muscle never gets into the descending limb?
No. So let me clarify one thing. That force length relationship I showed you was measured by looking at muscle after it's been extracted from the body. So it's not connected to any bones, and so that's how they can make this measurement. All right. So let me quickly summarize, and then we'll do some review questions, right? What I gave you last Friday to work on. So fatigue is immediate, while delayed onset of muscle soreness is going to be delayed and it lasts longer. We talked about isometric, eccentric, and concentric contractions, how it's going to be based on changes in muscle length, and also it depends on the load, whether the load carried by the muscle is greater than the force generated by the muscle. And we also talked about differences in force gradation in skeletal and cardiac muscles, and the reason for these differences is due to structural organization, nerve input, and also the contractile proteins which are within the cell. So in this regard, we talked about motor unit recruitment and twitch summation, which are both unique to skeletal muscles, and we saw that the force-length relationship is common to cardiac and skeletal muscle, but the region where the cardiac and the skeletal muscle function physiologically is different. The cardiac muscle functions in the ascending limb, whereas the skeletal muscle functions in the plateau region. So let's quickly go through some of the questions from what I gave you on Friday. So stimuli from the central nervous system is not required for blank, and the TAs don't need to worry about this. We're going to go through it pretty quickly. All right. Stimuli from the central nervous system is not required for motor unit recruitment, twitch summation, force-length relationship, none of the above. Okay, we got 40 responses, more than 50, great. So most of you said force-length relationship, and that is correct, right? So a stimuli from the central nervous system is not required for the force-length relationship, especially when you consider the functioning of the cardiac muscle. Okay, the blank muscle is more sensitive to changes in the muscle length than the blank muscle because it functions in the blank of the force-length relationship. Yes? Oh, okay. Give me the answer. How many of you think it's A, B, C, okay, D? Alright. So, the right answer is C, because the cardiac muscle is more sensitive to changes in muscle length because it's functioning in the ascending limb. Okay, so let me go through the remaining questions from what I gave you on Friday. Okay, the connective tissue surrounding a muscle bundle is referred to as blank. Epimysium, endomysium, perimysium, or is it a tendon? What surrounds a muscle bundle? So these are questions which I will not be going through the Monday before the exam because you're going through it now. Alright, so pay attention. Okay, most of you said perimysium. And perimysium is the right answer. Right? It's going to cover the muscle bundle. Epimysium is what surrounds the entire muscle, and endomysium surrounds individual muscle fibers. Okay, cross bridges permit thin filament to transition from the blank to blank state. What do cross bridges binding result in? Is it blocked to closed, closed to open, open to closed, open to blocked? Okay, we have, okay, most of you said close to open, and close to open is right. Notice here that it's cross bridges binding which causes the thin filament to transition from the closed to open state, because the weakly bound cross bridges, they're going to bind strongly and push tropomyosin further along the thin filament. Okay, arrival of the stimuli at the presynaptic cleft of the motor neuron will release acetylcholine to activate blank. Is it ligand-gated sodium channels, voltage-gated sodium channels, ligand-gated calcium channels, voltage-gated potassium channels? Okay, most of you said ligand-gated sodium channels, and that is right. So the opening of the ligand-gated sodium channels will cause this initial threshold to be reached, which will in turn trigger the action potential in the skeletal muscles. Okay, here's a similar question. Fish hunting snails inject toxins into their victims that block acetylcholine receptors at the neuromuscular junction, and that can cause paralysis. So the toxin is most likely blocking which type of channel? Is it ligand-gated sodium channels, ligand-gated chloride channels, voltage-gated calcium channels, or voltage-gated potassium channels? What channel would be blocked at the neuromuscular junction? Okay, most of you said ligand-gated sodium channels. I'm very happy. That is the right answer. Same principle as the previous question. Okay. Okay, next question. Blank binds actin in the absence of calcium to prevent actin-myosin interaction. It is troponin T, troponin C, troponin I, or tropomyosin. What is going to bind to actin in the absence of calcium? Okay, most of you said T and C. The correct answer is troponin I. Okay, let me explain why. So I told you troponin I is the inhibitory subunit which will bind to actin in the absence of calcium, and I even showed you here's this actin binding domain in troponin I. But the moment calcium binds to troponin C, notice that this hydrophobic pocket opens and TNI is no longer binding actin, but it starts to interact with the troponin C subunit. Alright, so the right answer is troponin I. During rigor mortis, calcium will flood the thin filament because of blank. Why will calcium flood the thin filament? Is it because circular pumps can't function properly, ATP cannot bind myosin, ryanodine receptors cannot function, dihydropyridine receptors are inactivated? The right answer is actually because circular pumps cannot function. That's why calcium is not inside the sarcoplasmic reticulum, but it starts flooding into the thin filament. Okay, let's do one last question. A mutation in the myosin heads prevents them from binding strongly to actin. In this situation, the transition from thin filament from blank state is impaired. So if myosin can't strongly bind with actin, what is impaired? Should be straightforward, guys. Option C is right, closed open state is affected. Okay. Alright, we have one question on smooth muscles. We'll do it when we come back on Wednesday. Thank you all for your time. Testing.